we studied the Hilbert space on the two-sphere with some in Wilson line insertions. But I didn't really explain how to analyze the Hilbert space of Chern-Simons theory on some other two-dimensional manifold. What I want to do today is to explain the general procedure of how one does this. It actually fits really well with what Aldo said yesterday about the co-adjoint orbits. So did you explain how one finds the Hilbert space out of a Wilson line from the co-adjoint orbit, or just go to the Lagrangian?
No, not so much.
Okay.
And briefly, I mentioned something.
With the quantization and yeah, okay. So I'll go into that a bit more detail. So in general, and we remind you of something I mentioned the other day. For any quantum field theory, on, say, some manifold cross or we think this is space, and this is time, and the signature for this discussion, whether it's Euclidean or Lorentzian signature, actually doesn't really matter very much. The Hilbert space is defined as follows. So firstly, you define equations of motion on M to be the set of gauge equivalence classes of solutions to the equations of motion on M cross some very small interval where epsilon is very small. And the second part, which I want to discuss today, is to notice that this manifold, typically an infinite dimensional manifold, has a natural closed two-form and in coordinates we can find coordinates p and q such that omega looks like this. So such a two-form is called a symplectic form. So normally if I take a closed two-form, you can always expand it in some way, but I might not be able to find coordinates such that it picks up every single coordinate, like every pair, that all the coordinates are paired in this way. So that's a non-degeneracy condition, like the invertibility of the metric. So this is, you discussed symplectic forms a little bit yesterday, right? And then the third step is that the Hilbert space is defined using omega by something called geometric quantization. So the thing I'd like to explain is, where does this two-form come from? Well, what we're going to find is that for most theories, and here there's a slight subtlety at this point for Chern-Simons theory, but we'll deal with that when we come to it. Omega is equal to d alpha, where alpha is a one form, alpha looks like some PSI2019. So what I want to do is use the Lagrangian to build this one-form alpha. Alpha is called the variational one-form. So here's how it works. Well, suppose I have a field. I'm not going to say exactly what kind of field theory I have. But if you want to be concrete, you can imagine that this is a scalar field on M times an interval, which satisfies the equations of motion. The tangent space to the space of solutions to the equations of motion, well, that's the first order variations of phi. The cotangent space is a linear dual. So an element of the cotangent space is something which takes a first order variation and gives you a number. Is equal to the set of functionals, the linear functionals, d phi Now, whatever a one form is, the kind of thing we're trying to build, it's an element of this space for every phi. One form, so alpha is an element of this space for all phi. So that is, alpha is something which takes a field phi and a first order variation delta phi and gives us a number. So this is just, I'm writing on a space of fields which satisfy the equations of motion, something that you know already. So what's a covector? It's something which a one form on a manifold is something which takes a point on a manifold and a vector at that point and gives you a number. And this should be linear in this first order variation. Okay, so this is the thing we want to build. So any questions? So let's explain how to build it. So, as I said before, this is very special. Yep. the way we're going to build this, it uses the fact that the equations we're studying are variational equations. So this one from alpha is going to be built using the Lagrangian. So we let L phi be the Lagrangian. I'll give you some examples in a minute, so for now, I'll just keep it abstract. This is an n form on m times the interval, where dimension of m is n minus 1, because it's the Lagrangian density. It's something I can integrate over space-time. Now, if I vary phi, I can look how the Lagrangian varies when I vary phi. L phi plus delta phi looks like delta phi. So by the definition of the Euler-Lagrange equations, if I vary phi, I'll pick up delta phi times the Euler-Lagrange equations for phi. But as we know, when we study the Euler-Lagrange equations, we have to move things around using integration by parts. So plus the total derivative. Okay, so normally when we do the Euler-Lagrange equations, this total derivative doesn't matter. But for us, this is the part that will be essential, because we're studying what happens on M, which we can think of as the boundary. Yeah?
What is n? The m bigger than n minus 1?
N is
Dimension.
the dimension of this whole manifold here.
N is the dimension of m cross minus epsilon comma epsilon.
Yes. So n minus 1 is the dimension of M. Okay. So it's the first, this total derivative is the thing we're going to care about. So firstly, we note phi satisfies the equations of motion. So the first term vanishes. And so let's write the total derivative as L boundary, that's L tilde by delta phi. And this is an n minus 1 form. So take that back. Where the total derivative is d. To be a total derivative must be d of an n minus 1 form. So I'll write it as d of L tilde, where L tilde over phi is an n minus 1 form. So now we know, we can kind of see what is our alpha. It's just the integral of L tilde. Alpha by delta phi is the integral of L tilde by delta phi. Okay, so this is a little bit abstract. So let's look at a couple of examples, and we should recover really familiar things. For quantum mechanics, you'll find dp/dq. Quantum mechanics, M is a point. phi is a function on the interval. The Lagrangian is integral phi del t squared phi. Now, sorry, stop the integral. The Lagrangian is phi del t squared phi. So if I vary the Lagrangian, L of phi plus delta phi is equal to L of phi plus delta phi del t squared phi plus phi del t squared delta phi. Now, if phi satisfies the equations of motion, so that its second derivative vanishes, this. Sorry, I'm going to move this into your side. I wanted the variation of that. Sorry, I should have had. When I wrote it earlier, I shouldn't have had L of phi plus delta phi. I should have had minus L of phi because I wanted how it varies. I wanted the derivative of the Lagrangian. So sorry about that. So phi satisfies the equations of motion. This is then phi times del t squared delta phi. Well, now if we were allowed to integrate by parts, I would move this derivative over here and then do that twice and use the equations of motion to show that vanishes. So let's write that out carefully. So it's del t of phi del t phi delta phi. Del t of phi del t delta phi minus delta t phi and this part goes away. Okay, did I get that right? Yeah. So this tells us L tilde is equal to the term inside these brackets. Phi del t delta phi now so phi satisfies the equations of motion, so it can be written as something satisfying the equations of motion. It's very simple. It's just P plus T times Q, like Q plus T times P. So phi is Q plus TP. So this expression here, when I integrate it at t equals 0, at t equals 0, L tilde gives Q delta P minus P delta Q. Which is great, so that this is the variational one form, and the two form, it is d of it, is the right one, dp dq, or 2 times dp dq. And then omega is equal to, say, minus 2 of T. Okay. Any questions about that calculation? As you see, it's pretty easy. And the only content is just you pick up the integration by parts term, and you turn this into the symplectic form.
Would this be in generally? I mean, this total derivative term has to do with our Nutter theorem or our conserved currents. So would that be in general the case that L would just be the conserved current?
Conserved current for what?
Oh, that's true.
It is related. There is a related computation which will give you the Hamiltonian. But this is not the same because if you think about this one carefully, I didn't really need to choose coordinates on t. Like to do the Hamiltonian, I need to choose a direction which is time. That gives me the Hamiltonian. Here, this just could have been any n manifold with boundary, and I would have got this. Okay, so let's quickly do a few more examples. If we do a scalar field in dimension n, and so phi is a function on m times minus epsilon epsilon, and the Lagrangian is phi, the Laplacian on m of phi plus phi del t squared phi. Well, actually, this case is just exactly the same. The reason is we assume m has no boundary. So total derivatives in the m direction these can be discarded. Because ultimately we're going to integrate over m. So if I have d of something in n minus 2 form along m, it doesn't matter. So we're really only integrating by parts along time. Parts along time, we get alpha is the integral over m of the same expression. Okay, so let's do one more example. You have fermionic field. on m times an interval. So the Lagrangian looks like L is psi times the Dirac operator of psi, which is equal to psi gamma 0 del t psi plus psi, the Dirac operator along m of psi. So this term has no time derivatives, and this term only has time derivatives. And as a first order derivative, there we find alpha, the one form, is the integral around m of psi gamma 0 delta psi. So the fermions don't split into P and Q in the same nice way. All the components of the fermions are really on the same footing. Okay, so the next thing we want to do is to study this Bertrand-Simons theory, unless there's any questions.
Sorry, what was the last remark? I didn't catch it.
Oh, so here we don't really split things into P and Q. So for example, like say omega is the integral over m of delta psi gamma 0 delta psi. It's not like dp dq in general. So for instance, if you wanted to, as I'll see later, if you wanted to choose a boundary condition, that's what's called a Lagrangian submanifold, where you set half of the variables to 0. That has to, here you would set half the fermions to 0, whereas here you could have set p equals 0 or q equals 0.
So we don't have a notion of conjugate variables in the fermionic?
Yes. So if we were doing fermions in one dimension, we would find it's a Clifford algebra. The algebra is a Clifford algebra generated by psi I with the relation that the anti-commutator I psi j is delta j. And this whole thing is a symmetry of SON, so you can't split it up into raising a lowering operator without breaking the symmetry. Mm-hmm.
So if we don't have conjugate variables, how can we define this symplectic form?
So in this case, the symplectic form is like e psi I, e psi j, delta ij. So we know these are fermionic variables. So the symplectic form is supposed to be anti-commuting, but we pick up an extra sign because they're fermionic variables, so it's okay that it's a delta j. So it's just not, it's a fine symplectic form, it's just not written as dp dq. If you wanted to write it as dp dq, you would have to say, suppose we had two fermions, then you could change basis and say psi plus is like psi 1 plus I psi 2, psi minus equals psi 1 minus I psi 2, something like that. And then you would get the symplectic form looks like psi plus, or psi minus. But this choosing this basis does not respect all of the symmetry of the problem. Well, this is dimension 2 is a bad example because it actually does. But If there was 4 variables, it would not respect all the symmetry, because then spin 4 would be broken to SU2. And actually, the same phenomenon will happen in translated series. So it's so let's take M to be the 2 torus, and coordinates theta 1, theta 2. We can ask, we take the group to be U1 to start with, then the space of solutions to the equations of motion on G2, this is equal to the gauge equivalence classes of flat U1 bundles. Now, there's natural functions on this space. So if I take my torus, I can ask, what is the Wilson line around that, or the Wilson line around that? And these provide coordinates on this space. So this space is also a torus. Which we can think of as U1 times U1, where I can take the exponential of the integral around U1 of A, that's an element of U1, and the exponential of the integral of U2 of A is another element of U1. Yep.
Sorry, what is a flat bundle, like with flat connection or no?
So, sorry, flat means the curvature vanishes. So let's choose coordinates on this U1 times U1. So I'm going to choose, it'll be convenient to choose multi-valued coordinates. Say lambda 1 to be the integral, and lambda 2 to be the integral of U2 of A. So these coordinates are really the logarithms of the natural coordinates. So as I move around, they kind of glue together. In other words, they have periodicity.
So does lambda 1 and lambda 2 coordinatize without being multivalued, coordinatize the flat U1 bundles without taking the gauge quotient?
Yes. So lambda 1 and lambda 2 coordinatize the flat bundles for the group OR. And then there's extra gauge transformations, the group 1, which make those identifications. But on a little, So the space of flat bundles is also a torus. And if here is the base point where the gauge field is trivial, lambda 1 and lambda 2 are perfectly good coordinates on this little patch there. Or indeed on any other little patch. And maybe e to the 2 pi I lambda 1 are the better known coordinates. Okay, so what? So let's do our calculation. So what is the 2 form? Well, I can take any gauge field A, and it's working near the trivial gauge field. We can write any A solving equations of motion as lambda 1 d theta 1 plus lambda 2 d theta 2. So the Chern-Simons Lagrangian is ADA so it's going to be pretty clear what we're going to get if I do a first order variation of A. That's delta A dA plus A d delta A. So that's delta A dA plus d A delta A, which is minus plus dA delta A. Now, if A is a flat connection, so dA is equal to 0, so the Chern-Simons Lagrangian, the variation of it, I forgot this term, is equal to d of A delta A minus 9. So this expression is the variation in one form. So now, all we have to do is write A like this and C to describe it in terms of the variations of lambdas. And it will be very easy. So inserting A is lambda 1 d theta 1 plus lambda 2 d theta 2, so that delta A is delta lambda 1 d theta 1 plus delta lambda 2 d theta 2. We find the one form alpha is minus integral over the 2 torus a delta a equals minus integral over the 2 torus. What do we find? We find lambda 1 delta lambda 2 minus, if I do a wedge delta a, it's lambda 1 delta lambda 2 minus delta lambda 1 lambda 2. Okay. Since these lambdas are constant on the torus, so up to a constant, and I'm always going to have trouble normalizing these constants. It's up to a constant is and therefore the Q form omega is delta lambda 1 h delta lambda 2. Okay. So to sum up, what we found, not being very careful at calculating the constants, is that this natural 2 form on the torus, which parameterizes these solutions of the equations of motion, is just the volume form on the torus. And if we normalize things correctly, the integral of this normalization integral over T2 of omega is equal to K, the quantized Chern-Simons level. Any questions? So Aldo said a little bit yesterday about why these things are quantized, right?
No, not really.
No, really?
Just say it like this.
Okay. So I wanted to be able to get to computing the Hilbert space, but I don't think we're going to be able to do that. No, maybe we can start doing that. Yeah. So given a manifold X and a symplectic form, omega, then the procedure called geometric quantization produces a Hilbert space. So how does this work? Okay, well, let's start the case X is order 2n. And omega is some dpi y to dqi So in this case, we define Zi to be Zj Pj plus square root of minus 1 Qj. And this, if we do this, we identify OR2n with Cn. And the important feature is that omega has nice behavior in these coordinates. So omega looks like, I think, 1 over 2I sum dzi wedge dz bar I. So this is the kind of picture we're going to generalize. We're going to say whatever my x is, I want to define complex coordinates like this, which locally make it look like Cn, so that omega looks like dz bar. Well, then the Hilbert space is functions of the z. So it's holomorphic functions of P and Q. Let's see. Holomorphic functions of z bar, i.e. functions of P and Q, which satisfy the Cauchy-Riemann equation.
Is this the definition of Hilbert space that we must have a holomorphic function?
That's what it said?
Why we say it's holomorphic function? Is that
Well, so perhaps you would have been more familiar with the story where I would take functions just of, say, just of Q, right? That would be, I say, L2 of Q. That's the standard thing done in quantum mechanics. They're very closely related. So roughly, so if you take, so you would, so I'm setting it up, I want to look at functions which do not depend on z bar, whereas the standard thing in quantum mechanics would be look at functions which do not depend on momentum and only depend on position. But you know that in quantum mechanics, I could have also said, let's take those functions which only depend on momentum and not on position, and it's the same by the Fourier transform. So there's integral transforms which relate any way of, given any way of choosing half the variables, they're all kind of the same by versions of the Fourier transform. This one is the one that works on curved manifolds, basically. So, the Hilbert space there, well, they satisfy the Cauchy-Riemann equations, which is okay, so does this description for quantum mechanics make sense to everybody else? So let's So what happens globally? So if we have a manifold X, and if globally our 2 form is d alpha, where alpha is a 1 form, then we do the same thing. That is, we choose holomorphic we choose a complex structure on X which is given by coordinates zi bar locally, with the feature that the change of coordinates is holomorphic. And then we also assume that locally omega can be written as some Gij Bzi with Bzi or j, and then the Hilbert space is defined to be the space of holomorphic functions on X. So that is, in this case, when we make this assumption that globally omega is d of a 1 form, which does not happen in Chern-Simons theory, because in Chern-Simons theory, the 2 form is the volume form of the 2 sphere, but is not d of anything, because its integral is non-zero. Not in the 2 sphere, on the 2 torus. Under this assumption, all we do is we just look at holomorphic functions on X. So if we were studying the 2 torus, this ansatz would lead to studying holomorphic functions of the 2 torus. But in the case when this does not hold, when omega is not equal to d alpha globally, but only locally on X, then this is, for example, X is d2, and omega is d lambda 1 twice d lambda 2. Then this ansatz only works locally. And the gluing rules are changed. So I'll say more about this next time. But what we're going to find if we look at the example of T2, what we find next time with this omega, well, if on each patch, for example, if I view T2 as a quotient of the plane by a lattice, then on that plane, like locally on that plane, I can write omega as lambda 1 d as d of something. But on that plane, this piece here will not be periodic. So when I study the holomorphic, on that plane, I'm going to be studying holomorphic functions on the plane, but they will not be holomorphic functions in the torus because they won't be quite periodic anymore. And you will end up studying things like theta functions. And so so the general story we will find is that abelian-Chern-Simons theory for any Riemann surface, the Hilbert space is always expressed in terms of some kind of 19th century type special functions, okay, like theta functions on that surface. Okay, stop there unless there's any questions. Yeah.
So for me, it's very abstract to see this Hilbert space as a space of holomorphic functions or defined by these holomorphic functions. So I don't know if you can say a little bit more about why this is a Hilbert space.
We could maybe do a tutorial on the Bargmann representation.
On the Bargmann representation? Yeah. That would be that's actually a really good idea. I mean, that
would explain what.
Because you can see the raising and lowering operators acting on this space. Is that what you mean?
I think so.
Yeah. I mean what to say? So up to linear transformations P and Q, they're related to Z and Z bar. So Z and Z bar should have the same canonical commutation relations as P and Q, because omega is also written as Z Z bar. So on this Hilbert space, there's raising and lowering operators given by multiplication by Z, and Z bar again has sent to differentiation with respect to Z. So if I just look at holomorphic functions, suppose I'll just look at those holomorphic functions which are polynomials in one variable, like Z through K. And there's a vacuum vector 1, and these are obtained by hitting this with, I have Z, del Z, they're raising and lowering operators, and every state is obtained by hitting it with this guy. So that's like a pretty familiar Fock representation. And this is just the same thing with many.
Can one use omega to these Hilbert spaces with an inner product?
Yes, great question. So what will happen is so this story describes field theories which are not time reversal invariant. So when we say Hilbert space, the concept of Hilbert space, I think I've put this before, is tied to the fact that applying time reversal is the same as applying complex conjugation. So time reversal is I take my vector space, the space of states, I take its dual. In complex conjugation, well, it gives me, then I get a Hermitian inner product. So these theories are not time reversal invariant in that sense. However, you can tell that doing time reversal invariant, like reversing time, sends omega to minus omega plus a particular constant. So for particular values of omega, yes, you can get a Hilbert space. Like there's some very special coefficient there.